Okay, so good morning to everyone. Today is Monday, and on Friday we are not going to have a class because it's going to be holiday. So let's see, first of all, what we need to do today. So last Friday, we saw the simple harmonic motion and the energy conservation. I'm going to review a bit more what we did last time. And then we are going to go to the single pendulum, which is what we are supposed to discuss today. But because then on Friday we do not have any class, I want to go through also mechanical waves and wave speed. So let's see what we can do about this topic, and the rest then we will catch up next week, the following week. Then on next Monday, there's going to be the midterm. So the lectures that cover these midterms are 25 to 32. So essentially until the pendulum. So after the pendulum, the things that we will see later after the pendulum are not going to be part of the midterm, okay? And 25, let's see what was 25.
It's essentially a rotation, fluids, and oscillations. That's it.
Rotation, exactly, all the part of rotation, fluids, and then we have oscillation until the pendulum. Let's see, maybe we don't do anything of this one. We will see.
That's right. That's right. Waves is not on the
wave is not part, so I don't want to confuse you. Let's see where we get. Okay, let me now share this. Okay, so what we saw last time we saw that the connection between the uniform circular motion and the simple harmonic motion. So we defined the position as a function of time as x is equal to a cosinus of theta. Theta, we defined that is equal also to omega t, where omega is the angular velocity, and t and omega, sorry, we know that is 2 pi divided by t, capital T, where the capital T is considered our period. So the time that it takes to do an entire circle or to make an entire wave. So the angular frequency omega is also 2 pi f, where f is the frequency, and we know that is 1 over the period. So the units for omega is radian per second. While remember, the period is a second because it's a time, and the frequency is second to the -1, which we called hertz. Now we also saw that this harmonic motion can be provided also by a spring. And the mass of a spring is proportional to the displacement and also to the acceleration. So from this equation, if we substitute the time dependencies of A and X, and you don't care about these things, I mean, if you want to see, is indicated here how you can find it. But what is important for you is this formula here. So where the angular velocity that we saw before is the same omega that you find in this equation here. When you have a spring, then this omega is also equal to the square root of k divided by m, where k is the coefficient of the spring and m is the mass attached to the spring. So we saw also some other properties last time. We saw that here we have our plot for the positions versus time. We said already that is a cosinus, so the position x cosinus a cosinus of theta, and here indeed we have the expression of a cosinus. So here we have that we start from a, which is the amplitude of the oscillation, and so our oscillation will go between a and -a, called the amplitude. And here we are at the beginning, and as the time passes by, this is the equation of the motion is written here, and this is the plot. Then for the velocity, instead, is a sinus. And so because of that, you see that we have a different plot. And you see it starts from 0, because when we are in the position A, of course, we have 0 velocity. We're it's still in that position, and then it starts to move. And so we see how it moves. And the period T is from one top of one of these crests to another top. So this is the period. And after that, the wave repeats itself all the time. So the maximum velocity here, because we have the, so let's see, A is cosinus of omega t. Omega, we know that is 2 pi divided by the period. So we can write it as 2 pi t divided by t, the capital T, the period, which is also equal to A cosinus of 2 pi frequency t. Because indeed, omega, we know that is 2 pi t, or 2 pi, the frequency. Then x dt is equal to A cosinus of omega t. We also know that the velocity is minus omega A sinus of omega t. So when is the velocity is going to be maximum, is maximum when sinus of omega t is equal to 1. So essentially, velocity is maximum where it is equal to omega A, which is 2 pi, the frequency, multiplied by A, or if you have the period, is equal to 2 pi A divided by T. So these are the equation to be able to find the maximum velocity. Okay. And the maximum velocity, you essentially have it in this point here and here, which correspond to the point where you are closer to equilibrium position. So imagine with the spring, you are taking the, extending the spring up to a position A, you open your hand, so you leave the spring to move and your object to move, and the maximum velocity is achieved when is passing through the center, the origin of your oscillation. And then, so the equilibrium position, if you want, of your spring. And then, of course, we are considering that there is no friction, so the object will keep going in the opposite direction, minus A. And so, and will oscillate between A and minus 8. Okay. So those are the equations that I just told you before. X is equal to A cosinus of theta. This we already saw it. The velocity is minus A omega sinus of omega t. The acceleration is minus A omega squared cosinus of omega t. We also saw last time the conservation of energy. So in an ideal system with no non-conservative forces, the total mechanical energy is conserved. And so this is what we always knew from the past. The total energy is the sum of the kinetics plus potential energy. Kinetic energy, 1/2 mv squared. Potential energy, in the case of the spring, is 1/2 kx to the square. Now, since we know that the position of the velocity is a function of time, we can find the maximum kinetic energy and the maximum potential energy. So the maximum potential energy, the potential energy is this one, and we know that x can go between plus A and minus A at maximum, as shown by here. This is the maximum position of x. So we get that U max is 1/2 k A to the square. Doesn't matter if we are in the position plus A or minus A, because it's to the square, so the minus go away. So we have a positive energy, 1/2 k A to the square. And this is the potential, maximum potential energy. The maximum kinetic energy is when? Is when the velocity is maximus. So is when the potential energy is 0, right? And the kinetic energy is instead maximum. So we have 1/2 m A to the square omega square, because we remember V maximum, V max, here it is omega A. So in this case, kinetic energy is V to the square, so omega square, A to the square. Let me go back, where was it? Yes, here. A to the square, omega to the square. Or if you don't have omega, but you have K and M, then you have to, is 1/2 m A to the square. Here, omega was the square root, remember, of K over M. So if you do square root to the square, goes away, and you have 1/2 m A to the square K divided by M. And so you see the mass is here and is here, so we can remove it. So we can write it as 1/2 K A to the square, which is essentially independent from the mass of the object. So the maximum kinetic energy can be expressed in this way, 1/2 m A to the square omega square, if you know A or omega, or can be expressed in the case of a spring, and if you know the coefficient of the spring, as 1/2 K A to the square. Okay. If you have questions or things that we need to emphasize, let me know. So these were the extreme cases. The extreme cases, what does it mean? We have a maximum potential energy, and the maximum potential energy is where the kinetic energy is minimum, so is 0. Where is 0? Is 0 when the velocity is 0. So if the velocity is 0, we have 0 kinetic energy and maximum potential energy. So essentially here, here, here. And if we want to see, is when we are in A and minus A. Here we have the maximum of the potential energy, and we have 0, as you see, as velocity, right? 0 as velocity. So the velocity is 0 and the position is A, so we have maximum of potential energy. And vice versa, we have maximum velocity where the velocity is maximus. And here we have that the velocity is max in this point. If we go to look for where these points occur in the position, is when we are in the equilibrium. So here we have maximum kinetic energy, maximum kinetic energy, maximum kinetic energy. Here, maximum potential energy, maximum potential energy, maximum potential energy, and so on. In all the positions which are in between, how do I write the conservation of energy? I need to express everything. So here I'm going to write 1/2 K. I need to put the velocity. The velocity when it's not max, 1/2 m, remember, is A omega sinus of omega t. So in the reality, it's written in a different way. It's written here, but so is 1, because yeah, the kinetic energy is written after, sorry. So 1/2 K, because it doesn't write as omega A, but with the K, let me see, here you see is A omega, but we also see that the velocity, where is it? As a function of K, was written somewhere, or I forgot. Well, K omega, and anyway, is K divided by M, right? Keep in mind the square root of K divided by M. So if we go back here, here we have 1/2 m K divided by M. So the M goes away. A to the square sine square omega t. So this is the expression of our velocity. And here instead we have potential energy, which is 1/2 K, the position to the square, and the position is A to the square cosinus of omega t. So we can put these together, 1/2 K A to the square and cosinus to the square of omega t plus sinus to the square of omega t is equal to 1. And so we have that is 1/2 k squared. So the total energy is always constant as this value. And as the kinetic energy increases, the potential energy decreases and vice versa. And we saw that. So another way to see it, here is energies versus time. When U is at its maximum, K is at its minimum, and vice versa. Okay. This diagram shows how the energy transforms from potential to kinetic and back, vice versa. While the total energy is stable. This is the total energy. The sum of the two is stable, and we know that is equal to 1/2 k a squared.
Dr. Mindy, could I add something there?
Yeah, sure.
So everyone, this is actually pretty important, right? And this is analogous to a roller coaster that has no friction, where as the roller coaster goes downhill and its gravitational potential energy decreases, its kinetic energy increases. And the sum of those two, right? Total mechanical energy, which is K plus U, remains constant at all times. So if we imagine a mass on a spring that has no friction, no dissipation of energy, no what we call damping. When we're talking about an oscillating system, we tend to call it damping, like we do in lab. Then the total mechanical energy remains constant. And there's just this constant trade-off between the kinetic and the potential energy stored in the spring and the kinetic energy of the mass. Okay, so it trades off back and forth. So that's it. You know, even without the equations, that's an important thing to just understand conceptually, that that's what's happening with this system. Okay, thanks.
Very good, Mike. So let's look again at the situation. Here, the energy is K plus U. Are you able to see? Because it's a bit small. Oh. Here is all, okay. Well, the total mechanical energy is K plus U. But unfortunately, when I use this full screen, I cannot see, I do not see my finger where I'm pointing.
The pointer, yeah.
I don't know why, if it's me that I'm not capable of using it, or I don't know. So anyway, E is equal to K plus U, which is equal to 1/2 m dx to the square plus 1/2 k x to the square. And we just showed it before that is constant, okay? So this is kinetic and this is the potential. Now, let's review again what we said before. So in the position where x is plus and minus a, so when we are at the extremes, this is the position, zero position, the equilibrium. I move the mass of the object, so I stretch the spring until it gets to A, and then I open my hand. Right before I open my hand in A, here you see that the velocity is still zero, so we have all the potential energy. The energy is completely all potential energy. Then we open the hand and the velocity goes from zero, it increases, it increases, it increases until it gets to zero. So when we are in zero here, the energy is purely kinetic. And indeed here, the mechanical energy, the potential energy, A, the value of that before of X that before was A, now is zero. So the potential energy is zero. And then it keeps going and the velocity is going to decrease, right? The more it goes away from the equilibrium, the more it's going to decrease, decrease, decrease until it gets to minus A, and there the velocity is going to be equal to zero. So this is another way to see what we expressed before. So when X is equal to zero, kinetic energy is 1/2 m d to the square, velocity, maximum velocity to the square. So we have that, yeah, is a way to find again V max, which is A omega, or A, the square root of K over M. This is again a way to write omega F and T, the same one we have seen so far. And here we have the energy, and it's just a summarizing everything, anywhere we have kinetic and potential energy. At the maximum of this tension, so where we get plus and minus A, we only have potential energy. So all the energy is potential, 1/2 K A to the square. At the center, we have 1/2 mv max to the square at the center of oscillation. And then the energy is always constant. Okay, so this was a resume of what we already said. Let's see one example. I have a 500-gram block on a spring that is pulled a distance of 20 centimeters and released. The subsequent oscillations are measured to have a period of 0.80 seconds. At what position or positions is the speed of the block 1 meter per second? Okay, so what it gives us here is that the period is 0.80 seconds. So from the period, what can I do? I can definitely calculate the angular velocity. So the angular velocity is 2 pi divided by the period. So 2 pi divided by 0.80 seconds, which is 7.85 radian per second. Okay, now I have the angular velocity and the period. So we know that the velocity is equal to the square root of km a to the square minus x to the square. So we only saw before the expression, the km multiplied by a to the square, so multiplied by a when you are at the maximum. But when you are not at the maximum, this is the expression of the velocity. So here, which is also equal to omega A, remember V max before, where V max was omega A omega, okay? A omega. In the case of this was a maximum, but if it's not maximum, then you don't have only A, but you have the square root of A to the square minus X to the square. So here you have that the position X is equal to plus and minus the square root of this equation. And here at this point, we know how much is the amplitude, which is not centimeter. We have to bring it in meters, convert it in meters. So 2.20 meters to the square minus, here is the speed is 1 meter per second. So 1 meter per second divided by omega that we just calculated before. And so to the square. And so we have these two positions, X, where the speed of the block is 1 meter per second. So this was a pretty complicated one, Mike? Do you want to comment on this problem? Are they going to have problems like this?
Yes, this is something to understand. Yeah. Right.
Mm-hmm. Yeah. So
or vice versa, where you're asked to use that first equation to figure out the speed of the object at a particular position. Yeah, yes. One or the other. Yep.
Yes. So yeah, you see here, at least you have one example of a bit more complicated, because in this other case here, you are all the time, we were discussing before, all the time when you are in extreme condition, while here you are not in an extreme condition, you are just in a situation in between. And so also for the conservation of energy, remember when you are in a situation in between, you have to use this equation. Okay. So with this thing, I finish this topic and I go to the topic of today, which is the simple pendulum. So a simple pendulum, what it is, it consists of a mass M of negligible size, suspended by a string or rod of a certain length L of negligible mass. So here you see the pendulum. So you have this ball of mass m that is moving, and the pendulum here has a length, the string or the rod has a length L. So is moving back and forth and back and forth. And why this is connected to what we did so far. So imagine that you put pencil here in a way that the ball can really make a mark on a piece of paper, and you move the piece of paper. What you can see here is again the same motion that we discussed before. So you see here the single harmonic motion. So in this case, it's done by the single pendulum. So looking at for the pendulum, we can also look at the forces that are applying on it. And we have the tension here of the rope. If you still remember these things, you should remember them. It was not that long time ago that you did them. And then we have the weight going down. And then you have an angle theta here between the component of the weight along the tension here, along this axis, and a component along here, the perpendicular axis. Okay, so here we have mg cos theta and mg sinus of theta. So looking at the forces on the pendulum, we see that the restoring force, every time you move the pendulum here, it's away from the equilibrium position, right? The equilibrium position will be straight down. So the restoring force, which is like the restoring force that we were applying before with the spring had the restoring force every time you were moving the object, pulling the spring. And here is the same. You are pulling this ball away from the equilibrium position. So the restoring force is proportional to sinus of theta. So is this one that wants to bring back the ball here in the equilibrium position. Whereas the restoring force for a spring is proportional to the displacement. In this case, is proportional to theta, to the angle, okay? Now, mg minus mg sinus of theta is different from minus mg theta, but nevertheless, for angles that are very, very small, sinus of theta is very similar to theta. So if the angle is very small, we approximate sinus of theta with theta, okay? And so here, for example, in this one, we approximate sinus of theta with theta when the angles is very small. And this simplifies a lot, and I will show you later how. So substituting theta for sinus of theta allow us to treat the pendulum in a mathematically identical way to the mass on a spring. So therefore, we find that the period of the pendulum depends only on g and on the length of the string. So remember before we had that the period was 2 pi divided by omega. So omega was the square root of k divided by m. So if you do all the manipulation, all the changes that you need to do, you find 2 pi m divided by k. 2 pi m, our k in this case is mg divided by L. So we can write that the period for a pendulum is 2 pi, the square root of L divided by G. So T does not depend on the mass of the pendulum, but depends on what? On the length and then on the gravity constant, gravitational constant. Okay.
This, by the way, this is that expression for the period is used in the physics lab earlier in the semester without explanation. It's just sort of handed to everyone. And so now this is a short derivation that shows where it comes from. And like Dr. Bindi says, this is increasingly accurate. This expression for the period is increasingly accurate for small oscillations, right? When theta is very small, because that's when theta and sine theta have the closest agreement in their values. And the pendulum acts most like a mass on a spring. And then for really wide oscillations, it departs a little bit from this expression.
Yeah.
But we're not going to worry about that. We're just only going to deal with the small angle case.
Yes. So here I have one problem, one example. The period of oscillation of an object in an ideal mass spring system, so this is again mass spring system, probably I should have put it before, is 0.50 seconds and the amplitude is 5 centimeters. What is the speed at the equilibrium point? So the speed at the equilibrium point, you remember the equilibrium point is when our x went from plus and minus a to 0. So in the reality, we already know that is when the velocity is maximum. So we use the energy conservation at the equilibrium x equal to 0. Let's see if it's true. We just write all the equation 1 alpha mv squared plus 1 half kx to the square, because the equilibrium x is equal to 0. So this part here goes away. So we have that all the mechanical energy is equal to 1 half mv squared. Since our energy is constant, at the equilibrium, the kinetic energy must be at its maximum. So V is equal to V max, which we know that is all equal to A omega. So omega is going to be equal to 2 pi divided by t, which means 2 pi divided by 0.50 seconds, which is 12.6 radians per second. And the velocity, now we are able to calculate it because it's A omega, so it's 5 centimeters multiplied by 12.6 radian per second, which gives 62.8 centimeters per second. Is it clear? I think it's pretty straightforward after everything we said.
Yeah, I think so.
Okay, now here let's see a pendulum. So a clock has a pendulum that performs one full swing every 1 second. The object at the end of the string weighs 10 Newton. What is the length of the pendulum? So the period of oscillation for the pendulum depends on its length. We saw the equation before is 2 pi, the square root of L divided by G. So if I want to find L, L is equal to G T to the square divided by 2 pi to the square, which is 4 pi to the square, equal to G in 9.8 meter per second square. T was provided in 1 second, and 4 pi is, we know how much is 4 pi, so we find that it's 0.25 meter. So do you see that there is one thing in the problem that it was provided that we don't really care, the weights of the object, because we said before that L is independent here, that the period is independent from the mass of the object. So in the reality, we didn't use this information.
And that's one of the things that's verified in the lab experiment earlier this semester as well.
Very good. So now let's see an additional example. We have here 2 springs. Springs 1 and 2 in figure have spring constant of 40 Newton per centimeter and 25 Newton per centimeter, respectively. The object A remains at rest and both springs are stretched equally. Determine the stretch. So since the object here is in equilibrium, it says that the object remains at rest. The net force acting on it must be 0, giving so we have that F1 plus F2 is equal to Kx1 plus Kx2, which is 80 Newton. I mean, in the reality, here there is an error because it's not 80 Newton. 80 Newton is indicated here, sorry. Yes, 80 Newton.
Right, yep.
Yeah.
So this is in balance, right? This
Mm-hmm.
is Newton's second law. So, well, it's trying to say that the sum of all the forces equals 0, which means that the leftward forces must equal the rightward forces. Right?
Yes. So because here is 80 Newtons, so kx1 plus kx2 is equal to 80 Newton. So x is equal to 80 Newton divided by k1 plus k2. And so in this case, we have 80 Newton divided by 40 Newton per centimeter plus 25 Newton per centimeter. And if we solve this equation, we find 1.23 centimeter, which is the stretch of the spring. Do you want to add anything or it's fine?
Yeah, so this is if you stretch more, then both springs will pull harder and it'll be out of equilibrium. And if you stretch less, then the springs don't pull hard enough. And again, it'll be out of equilibrium. So we found the one distance where it's in equilibrium.
Yes.
One last thing I'll say is these two springs are in what we call in parallel. They're working in parallel, kind of like two horses that are hitched to the same cart side by side, right? If we had put one spring at the end of the other spring, we would call that in series. And I just want to sort of, I'm foreshadowing something that you're going to see in physics 152 when we put two capacitors next to each other in parallel or two resistors next to each other in parallel. It's a very similar arrangement. Thanks.
Thank you. Okay. Didn't we do that already? Yes, we did that already. So I can remove this. So in summary, for the simple harmonic motion require a restoring force proportional to the displacement. The frequency is the inverse of the period. The total energy is proportional to the square of the amplitude, as you've seen here, and the equation of motions are sinusoidal. Then we also have seen the velocity and period of a mass on a spring. So the velocity is plus and minus the square root of k divided by m, a to the square minus x to the square. The period is 2 pi, the square root of m divided by k. Velocity and acceleration of a mass in a simple harmonic motion, v is omega a cosinus of omega t. Acceleration is minus omega square a sinus of omega t. And remember also the equations for the pendulum. So they are the same, but the period essentially, sorry, here we have t is equal to 2 pi, the square root of L divided by G. Yes. Okay, with this, I finish all the part for the pendulum. Is there something that you want to add?
No, I think that's it. That's the end of essentially lesson 32.
Yes. And so all this part is what you are going to find in the next midterm. So in the last few minutes, if you have questions, we can answer your questions. Otherwise, I can introduce the topic of next week. Briefly introduce the topic. Any questions by anyone? I don't see any, so I'll probably do a few more slides. So next week, we are going to see the wave notion. So a wave pulse is a disturbance that propagates through a medium. So you probably have done this, maybe even a workout. I hate that workout actually, when you use the ropes and you, when you're both arms, you go up and down. It's a killer, but it's really good. So as you see, the wave propagates in the medium, right? So you started here going up and then it propagates, which means that it transfers energy without transferring matter. Matter is still the same, it's still our rope, but the energy is moving from the position of my hand until the end of the rope. So, and this energy is a combination of the kinetic and potential energy because it has a velocity, but we are also having a different I here with respect. Here it was 0 and here is a bit elevated with respect to 0. So we are changing also the potential energy. So wave notion and harmonic disturbance can set up a sinusoidal wave. The distance from crest to crest or through to through is called wavelength, lambda. So the amplitude we see before is the two extremes of the oscillation, goes from here to here, plus A and minus A, same of our simple harmonic motion we saw before. And now from crest to crest is this one is called lambda and is called wavelength, okay? And it has a certain velocity to transmit this wavelength from here to a different position. So such a wave will have a sinusoidal form in both time and space. Amplitude is going to be the maximum displacement. Wavelength, as we've seen, is the distance between points having the same phase. So is the difference between point like crest to crest, but also through to through, okay? So points that they have the same phase, what we call. And then the frequency is the number of waves passing per second. The period is the time of one complete wave to pass. So the relationship between the wave speed, the wavelength, the period, and the frequency. So the velocity is equal to lambda divided by t, which is also equal to lambda multiplied by the frequency. So again, period and frequency have exact same definition as you saw before. The motion waves might be either be transverse, which means that the displacement is perpendicular to the direction of propagation, or longitudinal, which means that the displacement is parallel to direction of propagation. Like, look at this one. So here we have this spring, and what we do is that the wave propagation is along x, plus or minus x, while here is like for the way the rope before. So this one is like in this case, essentially. So the displacement is perpendicular to the direction of propagation, while longitudinal is like if you squeeze, you see, you have a compression and relaxation. So in this case, you have that the direction of the particle motion and the direction of the wave propagation are the same, are parallel, okay? So this is the case of the rope. Direction of particle is perpendicular. I have to go perpendicular with my hand to move the rope. And this one instead is compression and relaxation. They are parallel. But then we also have a different type of waves, which are, for example, the water waves that might appear to be transverse, but they are actually a combination of transverse and longitudinal motion. So you have both of these, and you see something that is a bit more circular here. These are more our waves, right? The wave of the ocean are a mix of these two. There is both the transverse, so going opposite to the direction of the wave propagation, but also compression and relaxation. When two or more waves travel through the same medium at the same time, they also interfere in a process called superposition. I'm sure you have already seen this. For example, if you are in a lake and you just throw a stone that generates some waves, and then you throw a second stone that generates other waves, these two are superimposing. Or if you have with the boat, you are getting into the motion, the waves generated by your boat, motorboat, is they interfere with the one of the ocean, right? And so in this case, this is an illustration of the interference. using the principle of the superimposition. Here we have two waves exactly the same, you see, or maybe no, y2 is a bit higher than y1. So this is a bit higher than this one. And they have a different velocity, v1 and v2, and they are going one towards the other. So there will be a moment, initial moment, where the situation is like this. And when the time passes by, what we will have is that these two waves will start to interact one with each other. And so in the reality, the red curve, the big red curve, the thick one that we have here, is the superimposition of the two waves. And while they get even more closer to each other, we will see a bigger wave, which is provided by the sum of one and the other. And then after they pass each other, we will see that the waves will reduce, and then we will see two separate waves. So the displacement of any point in the rope is going to be the sum of the individual displacement. So y here is equal to y1 plus y2, okay? So in this case, for example, is the exact case that we showed before, but the only change is that y1 is equal to y2. These two waves are exactly the same. And so they are going one against each other. And here you see that you achieve double of the height. Okay, so this one, at this point here, you are going to have the y is going to be equal to y1 plus y2, which in this case will be equal to 2 times y1. And then they move in opposite direction here after they pass each other. But there is also, and in this case, we speak about interference, and we say that the interference is constructive because they sum up together, making a bigger wave. In this other case, instead, we will say that is destructive because, for example, here we have one wave, but here we have the wave that is in its opposite direction. Their velocity is opposite, but also the amplitude here, as we see, is going in the opposite direction. So when they get together, instead of being double, we are going to have the y, which is equal to y1 plus y2, because they are opposite to each other, is going to be 0. And then as soon as they separated, we are going to see this. So this is what we do for the noise canceling. The headset noise canceling essentially uses this method. And indeed, if you have, for example, is used for noise canceling technique. So here you have the original noise, and then the system generate an inverted wave so that the combined wave, they give a fantastic sound, removing the noise.
Hey, Dr. Mindy,
Okay,
I think we're out of time.
Yes.
So maybe if there's a good place to stop here, let's do that.
Yes. Perfect.